Today we will be talking about R-squared. R-squared is a one-number summary of how well a line fits to the data. To motivate that, let's look at these two graphs and ask ourselves the question, which line fits the data better? I'm gonna say most people would say the graph on the right. Now, why is that? Both times the relationship seems linear, but it looks like the residuals on the right-hand side are a lot smaller. So, well, maybe we can come up with a statistic that decides whether the fit is good based on whether the residuals are small or not. So, can we formalize that in the and find that from the regression output directly? So the next page here is giving some regression output. And so we see here on the left the familiar ANOVA table. We have the coefficient, standard error, t, p-value, and confidence intervals as usual. And so we were talking about small residuals, and the residuals are given here. Then here we have the sums of squares of the residuals, and their average is the mean squared error, which is given here. Yeah. So I can even highlight that, 3.99. So maybe we can just use the mean squared error as a statistic. Here is the other one. And the other one has a much smaller mean squared error, 0.266. And so that does seem to work, that whatever has a smaller mean squared error, that may be a better fit. So these both data sets were simulated from the same linear regression model. One had much more variation, and the regression model is listed there, y equals 3x plus epsilon. And one had a much larger standard deviation of 2 compared to the other one, which had a standard deviation of 0.5. But the problem with using sigma as a measure of quality of fit is that 2 may be large in one context and small in another. And we prefer instead a more standardized measure of quality of fit that fits between 0 and 1, so that we can say with 1 it's a great fit and with 0 it's not a good fit. All right, that's it for this motivation.